Hello, Physics 341. We have a test coming up, and here is a step-by-step guided solution key to the test review questions that we posted last week. So the first part of this was a matching the vocabulary on the left, the definition on the right. The first term that we're given is convex lens. Now remember, a convex lens is the one that bubbles out on both sides, and it is by definition, or by what it does, a converging lens. So all the light rays that come in, if they start parallel with each other, they're all going to be bent towards each other. So this is a converging lens. And the definition that fits with that, a lens that converges light that starts out parallel, is response F. Now based on that, you can probably figure out which one a concave lens is. It's the other lens, but just to jog our memories, it is the one that's shaped like an hourglass. Instead of light bending together, a concave lens is a diverging lens. So all these light rays are going to spread out, and no image is going to form over on the other side. So this is our concave lens, and this corresponds to answer C. The focal point, we already drew that convex lens up top. The light rays, we drew them as diverging together, and the point where that happens is called the focal point. So our focal point is the point at which rays bend together, or, if we have the concave lens, if we trace these lines backwards, the focal point lies on the other side there. So it could be where the rays are diverging from. If we look at our answer choices, we'll see that the focal point corresponds to answer D. Refraction is the process by which light changes direction when it passes from one material to another. So we measure these angles from an imaginary line. It's going to become important in just a second. And refraction is the process by which the light starts at one angle and ends up at another as it passes between materials. So we're looking for the process by which light changes direction from material to material, and that corresponds best to answer E. The critical angle occurs when I have an index of refraction material that is less than the index of refraction we started with. This means that light is going to bend away from this imaginary dotted line here. And what happens is, if light enters at the right angle here, we call this the critical angle, that the light is going to bend away from this line so much that it actually ends up trapped back in the material or reflecting inside. And that's what we call total internal reflection. So we're looking at the angle for which all light is totally internally reflected, and that corresponds to answer A. By process of elimination, we only have one word left. Normal must correspond to B, but the normal is in fact the name of this dotted line here. It is the line from which all angles are measured. And it's called the normal because it is perpendicular, which is the normal is a more mathy version even than perpendicular. That means perpendicular. So this line is always perpendicular to the surface. It's perpendicular to surface. And it's important to remember that all of our angles are measured from this normal and not the other way around. We're not going to measure this angle. We're going to measure it from the normal down to where the light ray is. All right, that does it for the matching. This next part, we have light bends towards the normal when the second material has a greater index of refraction than the first. So drawing a picture is very, very key to these kinds of problems. If you're not drawing a picture, starting your problem off by drawing a picture, you're doing yourself a real disservice. So here we have light bending towards the normal. So the angle starts one way and it gets tighter, bent more towards the normal, when N2, the second material, has a greater index of refraction than N1. So we need N2 to be greater than N1. The way I like to think about it is you can generally correlate, it's not the same thing as density, but a larger N value means a denser material. So this could be air up top and glass down at the bottom. I like to think of light gets really like tight and squished as it enters a denser material, and it has to conform closer down to this normal line here. Total internal reflection can only occur, we talked about this a little bit during the matching part. Light bends toward the normal when N2 is greater. In order for total internal reflection to happen, the light coming in has to bend so far away from the normal that it gets trapped back inside the material. We said in problem 7, light bends toward the normal when N2 is greater than N1. In order to bend away from the normal, you have to have N2 less than N1. Because light needs to bend away from the normal. So you will only get total internal reflection if you were going from a denser material to a lighter material. So this could happen between glass and air. It could happen between glass and water even. You have to go from a denser material to a less dense material. All right, moving on to problem 9. We have light entering glass of index of refraction 1.45 from air, and we want to know what the speed of light in the glass is. Well, this sort of question is asking about what the definition of the index of refraction really is. N is a ratio of the speed of light in a vacuum, C, to the velocity, the speed of light in the material. So light slows down when it enters a material, and N tells you by how much it slows down. If N is larger and larger, the light speed gets slower and slower in that material. So I want to solve for V here. In order to do that, the C is blocking my way to access to the V in the denominator here. So I have to pick up the C and put it over on top of the N. So C is going to come up and go on top of the N. So I get that V is equal to C over N. I'm going to plug in the values. C is a constant, 3 times 10 to the 8 meters per second. N is given in the problem to be 1.45. And when I put this into my calculator, I get a value of about 2.07 times 10 to the 8 meters per second. So it's a little more than a third of what it was in the vacuum. So key point here is that the index of refraction is the ratio of the speed of light in a vacuum to the speed of light in the material. If I want to know how fast light is going in any material, all I have to do is divide the speed of light in the vacuum by the index of refraction of that material. Now I have a little multiple choice question here. It says, what quantity stays the same for light entering a different material? Is it the speed? Well, we just said that the speed slows down when you enter a material, so it can't be A. No, light slows down. Is it the frequency? Maybe. Is it the wavelength? Maybe. Is it direction? No, we've definitely seen examples up here of light changing its direction as it enters the material. That's what refraction is. So that one's out. The trick is it is frequency that has to stay the same. The way I like to think about it is, remember, light is a wave, so light is vibrating up and down like a wave. So it's bouncing up and down, making a certain number of cycles per second outside of the material. When it enters the material, you can't essentially vibrate twice over here and only vibrate once over here, or vibrate more on the other side. The vibrations on both sides have to be equal, and that is the frequency. The wavelength, if we remember that the speed of a wave is related to the frequency and the wavelength, if the speed slows down in a material from air, that goes down. We just said V is constant, so no change there. In order to make this equation balance out, the wavelength has to get smaller as well. So the wavelength generally shrinks as you go from air to another material or vacuum to another material. So frequency stays the same. That's a very important concept that you should remember. All right. Moving on to the problems, the free response type problems. This is what you should expect in the not multiple choice part of the test. So here we have light incident. It's coming into diamond from an unknown liquid. So we have a liquid up top and we have diamond down at the bottom. Remember, pictures are going to make this a lot easier to think about. Diamond has an index of refraction of 2.42. It's very large. And light is coming in at an angle of 35 degrees. All angles are measured from the normal, so our 35 degrees is coming in there. And it bends toward the normal in the diamond to an angle of 15 degrees. We want to know what the index of refraction of the liquid is. So we don't know what n is. That's what we're trying to find. We do, however, know the incident angle to be 35, and we know the refracted angle to be 15 degrees. So we can use Snell's law, n1 sine theta 1 is equal to n2 sine theta 2. We know everything. We accept n1. We're trying to solve for this value here. So we can plug in the numbers we do know. The incident angle is 35 degrees. The index of refraction of diamond is again 2.42. And the sine of the refracted angle, we're going to put 15 degrees in there. So I divide both sides by sine of 35. I get 2.42 sine 15 over sine 35. I put these numbers in my calculator, making sure that I am in fact in degrees mode, and I should get a value of n equals 1.09. And that makes sense. The angle here is smaller. The light had to bend towards the normal in the diamond, so the index of refraction of the liquid had to be smaller than 2.42, and this number clearly is. That's a good sanity check you can do. Does my number match what the light is actually doing as it bends to or from the normal? All right. Next, we have a fiber optic cable. So this is the kind of thing that sends you high-speed internet. It starts at an N of 1.6 and enters a coating. So this is the outside of the cable. N equals 1.24. So a fiber optic cable, it's able to deliver such high-speed internet because essentially all of the signal gets trapped inside by total internal reflection. So we want this light to come in at a critical angle, and we don't want any of the light to escape. So all the light here is going to make a 90-degree or larger angle to be trapped inside. So we know the indices of refraction. We know the refracted angle is going to be 90 degrees. So we can set up Snell's law again. N1 sine theta 1 equals N2 sine of 90 degrees. If you recall that sine of 90 degrees is 1, then basically what we have is that the sine of our incident angle, which I'm going to call theta c for the critical angle now, is just equal to N2 divided by N1. We can plug our numbers in. 1.24 divided by 1.6. We want to really make sure that the number on top is smaller than the number on the bottom. If we have it the other way around, you're going to have a bad day. Your calculator is going to not know what to do with it. So make sure that you have the smaller number up top and the larger number down on the bottom. So we can do inverse sine of both sides, and our calculator will tell us that this ends up being about 50.8 degrees. So that's our critical angle problem. We know that no light can escape, which means the light has to bend away from the normal to 90 degrees or higher. So we set the refracted angle to 90 and then solve the resulting Snell's law equation. All right, lastly, we have a lens problem. We have a 7-inch tall photograph, that's our height of the object, is placed 34 inches away from a convex lens. So now our object distance is 34 inches. And the focal length is stated to have a value of 19 inches. I want to know what the image distance is and the image height. And I also want to know what are the properties of this image. So the image distance can be calculated by using our lens formula. 1 over f equals 1 over d0 plus 1 over di. So we have our object and image distances accounted for. We're going to plug in our values. 1 over 19 equals 1 over 34 plus the unknown 1 over di. I'm going to subtract 1/34 from both sides of the equation. And then I can put that into my calculator to get what 1 over di is equal to. And that should be equal to about 0.0232. I'm not done yet. I don't have di. I have to do the reciprocal of both sides of this equation to get that di has a value of about 43.1 inches. And based off this value, I already know one of the properties of my image. This is a positive number, and that automatically tells me that this is a real image. It's going to form on the opposite side of the lens, and I'll only be able to see the image if I project it onto a screen somewhere. All right, so we also need to know the image height. We need to get to the image height by looking at the magnification, M, of this lens. So the way we do this is we look at the negative value of the image distance divided by the object distance. We can plug those numbers in. We get 43.1 divided by 34, and this is equal to negative 1.27 times. This value here tells us the rest of our image properties. This negative sign here, this tells us that it is in fact inverted. Likewise, the fact that the number itself, 1.27, is greater than 1, tells us that the object, or the image rather, is 1.27 times larger, and therefore this is magnified. All right, so we now know the image properties. It is real, it is inverted, upside down, and it's larger than it originally was. We still need to find the image height, and that can simply be done by multiplying the magnification. It's 1.27 times bigger, so let's take our original height and multiply it by that. We'll get 1.27, we can leave the negative sign on if we want, times 7, and we get a final height of 8.89 inches. So there it all is. We found our image distance using the thin lens formula, the 1 over f formula. We found the height by getting the magnification first, and then using that magnification to multiply the original height to find how large the image will appear. And then we can use the fact that the image distance is positive to know that it's real. We use the fact that our magnification is negative to say that it's inverted, and the fact that our value of the magnification is bigger than 1 to tell us that it is magnified. All right, I hope you found this review helpful. Good luck on the test, and see you next time.